Okay, so last time we started talking about activation energy, and the equation that we put up for activation energy, we said K is equal A, the frequency factor, times E to the power of activation energy over RT. And we went over every variable in this equation. Now what we're going to do, so here is the activation energy equation. Now, I'm going to do something that we've done this before. And what I'm going to do, I'm going to integrate this. I'm going to integrate this formula to get a linear equation. Okay? And if I do that, then I can graph it. So we've done this before for integrated rate law. So I have this activation energy. I'm going to integrate this equation. Again, you don't have to know how to integrate for this class, but I'm going to give you the final product. I'm going to integrate it to get a linear equation to graph. Because when I have a linear equation, I could graph it. So if I do that, what I end up having is I want to end up having ln of k equals minus activation energy over R times 1 over T plus ln of A. Also, don't forget that another way to write activation energy, the abbreviation would be EA. Okay. Now, alright. Now, this looks familiar to you, right? Can you guys see the linear plot? Can we see a linear plot? Yeah. It would be y equal m for a slope times x plus b, right? That's my linear equation plot. That's my linear plot. Now, what does that mean? That means I can graph it. That means I can graph it. Now, you know how to graph this. We've done this before, so you know how to graph this. What I want you to do, I want you to graph this, and don't look at my graphing. You graph it and then check it with me after that. So, again, don't look at mine. Graph your own. So if you do this, my y-axis is going to be ln of k. Hopefully that's what you got. And my x-axis is going to be 1 over t. And then this is going to be my line. And what's going to be the slope? What is going to be the slope? What do you think? What is going to be the slope? The slope is going to be, minus activation energy over R. Because m is the slope. So this is my slope. So far so good? Okay. Alright, that's not bad. You knew how to do this. You knew how to do this. So this was an activation energy after integration in a linear equation. So we can plot this. Yeah? Okay. I want you to put a little circle around it. You gotta know this. Now, there is one more thing I want to go over with activation energy. And that is, what if you have two data points? What happens if we have two data points? If you have two data points, then it would be ln of k2 over k1 equal minus activation energy over R times 1 T2 minus T1. So, well, if you have two data points, this would be the equation. And I want you to take circle this one too, because you gotta know this equation also. And you use this when you have two data points, you're trying to compare. So far, so good? Okay. Now, let's do a practice problem. Let's do a practice problem. You ready? Here's a practice problem. A reaction is first order. Use the info below to obtain activation energy. Okay? Now here's the data. The data is going to give you half-life in minutes. I have 2.54 and 1.01. And the data is going to give you temperature in degrees Celsius, 25.0, 37.0. Okay, so what do we want to do? What do we want to figure out in this problem? We want to obtain activation energy. So we want to figure out what is the activation energy. Okay, now again, do you see in this scenario we're comparing, right? We're comparing because there's a different temperature. So we have a reaction, it's first order reaction, and then what's happening is you change the temperature. You change the temperature, and then we are going to compare. So the same reaction, we change the temperature, and then we are going to compare what happens to them. Yeah? Okay. Now, I know I have two data points. Do you also agree with that? So what I got here, I got two data points. I was like, okay, so it's the activation energy, and I have two data points. What that means is I have to use this equation. You following me so far? Okay. Now, using this equation, I have the two temperature to compare. R is a constant. I'm trying to figure out activation energy. But what else do I need? I need one more piece of information, and that is K. I need K. I need K. I need the rate constant. You following me? Okay. Again, I really want to make sure you understand to read the problem. So you read this problem, circle this. You're trying to figure out activation energy. This is the data table they give you. They change the temperature, they change the T. So what you're doing, you are comparing two data points. So you're comparing, this is your equation. And you have to be able to figure out activation energy, you can only have one variable, which means since T is given, R is a constant, you have to figure out what K is. Now, how are you going to figure out what is K? Okay. What other piece of information they give you? They also give you half-life. So if they give me half-life, can I figure out K? Yes. Because half-life for first order reaction is 0.693 over K, and then the first half-life equals 2.54. So the first K is going to be 0.2731 over minutes. Okay. Now the other equation again is a half-life for a first order reaction. So I put the equation for the first order reaction and is equal 1.01. Again, where am I getting these numbers from? I'm getting it from the table they give me, right? Every time they give you half-life, you can figure out K for a first order reaction. So what K is going to be is 0.686 1 over minute. Are we good so far? Okay. Let me put that nicer. Oh no, what am I doing? Ignore what I'm doing right now. I tried to make it nicer. That's gonna backfire. There we go. We're good? Okay. So now what I got the K value for the two data points. Okay. Now I need you to remember this. So this is the same reaction. It's the same first order reaction. But why do they have different Ks? This is the same first order reaction. It's the same reaction. Why does, even though this is the same reaction, when we have different T, why do they have a different K? The reason is, I need you to remember that K is temperature dependent, right? That K is temperature dependent. I need you to remember that. I need you to remember that K is T dependent. What does that mean? That means it changes with temperature. It changes with temperature. I'm actually writing here that K changes with temperature. So if you change the temperature, you are going to have a different K. And that's why we have a different K here. We're good so far? Beautiful. Okay, so now I have everything I need to plug in into my equation. And my equation is ln of K2 over K1 equals a minus activation over R times 1T2 minus 1T1. Okay? Now, here's what I need you to realize. And if you don't believe me, which is okay, I'm not going to take it personal, maybe just a little bit, that you can go, you're already home, you can do this both ways to convince yourself. It doesn't matter which one is 1 and which one is 2. So it's how it says K2 over K1 and then T2 minus T1. It doesn't matter which one you consider 1, which one you consider 2, as long as you are consistent. Okay? So if I figure out K2, if I say, for example, this one is K2, I have to make sure I use the same temperature. So it doesn't matter which one is 1, which one is 2, as long as you are consistent. Sounds good? And if you don't believe me, which is cool, just a little bit heartbroken, but it's okay. If you don't believe me, do it both ways and then see if you get the same number. And I promise you, you will get the same number. Okay. Now, what I'm going to do, I'm going to consider, let's see, what do I want to do? I want to consider this one 2 and this one 1. Again, it doesn't matter which one you consider 1, which one you consider 2, as long as you are consistent. So I'm going to consider this one 1 and then this one 2. Okay? So what that means is, all I'm going to do, I'm just going to plug in number. So it will be ln, my K2 is 0.273 over 0.686 equals minus, I don't know my activation energy. We said R is 8.314 times 1 over 298K minus 310K. How did I get those numbers? Remember, it has to be, since our R is in Kelvin, is joules moles Kelvin, the temperature has to also be Kelvin. So what I did, I just converted to Kelvin. How do you convert to Kelvin? You notice, you add 273 to convert it to Kelvin. Okay? Yeah, you guys pretty good with this? So now, the only variable that I have now is activation energy. So my activation energy is going to be 5.89 times 10 to the 4th. And that's going to be our activation energy. Okay, again, let's quickly review this problem. In this problem, what happened is I had 2 data points. Every time I have 2 data points, I'm comparing. I know this is the equation I have to use. Now, I was given different temperature, and I know at different temperature, you're going to have different K, because K is T dependent. So I have different temperature, and the half-life were given to me. Why did they give you the half-life? They give you the half-life so you can figure out K. Then you have temperature, you have the K, you have all the constant, you can figure out activation energy. And then all you have to do is just plug it in. Now, the last thing to really remember is that it doesn't matter which one is 2, which one is 1, as long as you are consistent, okay? As long as you are consistent. What do I mean by you are consistent? Basically, this K and this T were for the same set of reactions. So as long as you're consistent, it doesn't matter. Now, ready for the next thing? Before we move on, I need you to tell me, I know I can't hear you, but I want you to tell me anyway. What is the unit for activation energy? What is the unit for activation energy? You know the R unit from last lecture. You can go back to that lecture. So tell me, what's the unit for activation energy? The unit is joules per mole. Hopefully that's what you were shouting at me. The unit is joules per mole. Exactly. The unit is joules per mole. Sounds good? Okay. Now, guess what we're going to do now? We are going to do a couple practice problems. How do you feel about that? Yeah? Let's do it. I was going to give it as a take-home problem, but let's do it now. You can just pause me, do it, we're going to go over it. Let's do 2 really, really good practice problems. Alright, here's our first one. It's a long problem, but it's okay. It's a good problem. I need you to read this, okay? Now, you can pause me, you can read this. If you read this, here are the key things to think about. One of them is without a catalyst, and the other one has a catalyst, okay? Now, this one over here is without a catalyst, and this number over here is with a catalyst, okay? So this one is without a catalyst, this one is with a catalyst. Now, first of all, does this make sense to you? That should be the first thing you ask yourself. It was like, does this make sense conceptually? And hopefully your answer is, yes, it does make sense. Because the one without a catalyst has a higher activation energy, right? And the one with the catalyst has a lower activation energy. Because that's what a catalyst does. It lowers the activation energy. We're going to get more into it later, okay? That's why a catalyst, the reaction is going to happen faster, okay? So conceptually it makes sense. That's good. Now, here's the hint that I gave you. And I ask you, how many times faster is the one that is being catalyzed versus the one that is not being catalyzed? Now, do you agree that... Whoa, hold on. Let me read this. It's been one. Okay. And I'll also give you a hint. And the hint was, look at the ratio. Because you're comparing what is being with catalyst versus when you don't have catalyst. Yeah? Okay. Now, what type of problem is this? What type of problem is this? This is an activation energy problem. This is an activation energy problem because I give you the activation energy and I tell you the one that has a catalyst, the activation energy is lower than the one that does not have a catalyst. Now, I want to kind of review what we talked about, activation energy. What is activation energy? Remember, activation energy is a minimum energy required. Is a minimum energy required to, number one, to break bonds, because you have to break bonds in order for reaction to happen, to form new bonds. And it requires energy to break bonds. And also, you need minimum energy for atoms to collide. So, let's go there. So activation energy is a minimum energy required for breaking the bonds and also for atoms colliding. So far, so good. Okay. Now, the other thing I would do if I were you guys, I would write down the equation for activation energy. Okay. I would say, okay, there are 2 equations that I ask you to know for activation energy. One of them is K equal A times E to the power of activation energy over R, and the other one was ln of K2 over K1 equals minus activation energy over R times 1 T2 minus 1 T1. That's when you change the temperature and you have 2 data points, right? In this case, we have 2 data points and we are changing the temperature. What are we doing here? Which equation do we have to use? It's not this one over here, because we have no information about K whatsoever. And we're not changing the temperature, right? we're not changing the temperature. The temperature is remaining constant, okay? So we are not changing temperature. If we're not changing the temperature, then it's not this equation. So the only equation you're left with is the equation on top. Okay, hopefully you guys are following me. So again, every time I have an activation energy, I will write down all this equation. You know, activation is minimum energy required to break bonds, atoms to collide, so the reaction could happen. And these are the two equations you know. I know I'm not using this equation because temperature is not changing. This temperature is not changing. I am not changing the temperature. So I'm not going to use this one. This is the only one I have. And the hint that I gave you is like, look at the ratio. Look at the ratio because I asked you how many times faster. And I even give you more hints. I said put the one that is faster in your numerator. Okay, so let's do this. So I'm going to have a catalyzed reaction over uncatalyzed reaction because the catalyzed reaction is faster, uncatalyzed reaction is slower, equals frequency factor E minus activation energy over RT. Okay, and I'm asking you to compare them. So I'm going to ask you to look at the temperature. So far so good? Okay. Oh, and you know what I forgot to do? No one said anything. I forgot to put a T over here. Okay. Alright, now let's plug it in. Are you ready to plug it in? Now when you read this question, it says assuming the frequency factor A and the initial concentration of all reactant are the same. So what that means is, what I can do, I can cross out A. I can cross out A. Okay? If I do that, it's going to be E to the power of. Now, the activation energy for the catalyzed one was negative 187.2 kilojoules per mole. There is a problem. The R is joules. I am bound to my constant. The constant R over here is in joules. We talked about it last time. Is joules over Kelvin times mole. So because this is my constant and my constant is joules, I am bound to do that. The constant will dictate the unit. So what I have to do, I have to convert that to joules in order to work. 1 kilojoules is 1,000 joules. Very good so far. Okay. So that is minus activation energy over RT. So my R is 8.314 joules over mole times Kelvin. And the temperature is 300.3 Kelvin. I have to convert it to Kelvin. We're good so far. Okay. That was my reaction on top. Now on the bottom, I'm going to do the same thing. E is going to be equal, E to the power minus 367.8 kilojoules per mole. And I'm going to convert it to joules because my R is joules. That's going to dictate it. Over, I know it looks a little messy. My R is 8.314 joules over mole Kelvin times Kelvin has to be my temperature. Alright, it's a little bit messy, but it works. So, I plugged everything in. Now, this is all you have to do. After you plug it in, what I'm gonna get 2.76 times 10 to the 31st. Okay. Now, if I round this 3 times 10 to the 31st time. Now, what does this mean? What does this mean? Now, before you tell me that, I'm going to go back to this question again. So I'm giving you a question. and I give you 2 activation energy. One is the one without a catalyst, so it has a higher activation energy. The reaction is going to happen slower. The other one is the activation energy for a reaction with catalyst. It's going to be a lower activation energy because the catalyst lowers the activation energy. I'm going to get into that later. Okay, now if you can see that temperature is not changing. We're not changing the temperature. So it's not this equation over here with 2 points, which leave you with only one equation to use. And it also says assuming the frequency A factor is the same. So, and since you are comparing two things, I give you a hint, you should start with a ratio and put the one that is faster on top. Of course, the catalyzed one is going to be the faster one. So that's why I put this one on top. And the uncatalyzed one is going to be the slower one. Okay? So we did that. These are the 2 equations. I can cross out A based on the problem because they gave me that. Then I'm going to plug these in and divide by each other. Just remember that the R is joules over Kelvin mole. That means temperature has to be Kelvin and activation energy has to be joules. So I had to convert kilojoules to joules. So I get this number. What does this number mean? That means it's going to be 3 times 10 to the 31st times faster when you have a catalyzed reaction. That's crazy. It's so much faster. Can you imagine this? 3 times 10 to the 31st times faster than uncatalyzed reaction. That's crazy. That's really, really fast. And what this means that the way that catalysts work, catalyst lowers the activation energy. And we're going to talk about this in a couple lectures. We're going to talk about this. But I want to introduce here because it's kind of cool because you saw it with numbers. Without a catalyst, the activation energy is so much lower. And what happens? If the reaction is so much faster when that happens. Okay, this was a hard one. Hopefully you follow that. Okay, ready for next practice problem? Let's do it. The next one is really good. I could also be biased since I wrote the question, but I still think it's pretty good. Alright, pause me. Please pause me. Do this problem and then unpause me to go over it together. For a first order reaction, 2x going to y, the half-life is 3 minutes. What is the rate constant? Okay, let's do this problem together. Now, actually no, you do it first and then check it with me. So it's a first order reaction. That's good. I give it to you. That's good. Half-life is given. They said, what is the rate constant? Okay. Now, I'm going to write down the equation of half-life for the first order reaction. And the half-life is given is 3 minutes, so I can easily figure out K, which is rate constant. 0.231, 1 over minutes. That was easy. I know it's first order, I have the half-life, I can figure out K. So far so good. Okay. Now the next part is a little bit tougher. Assuming you start with 1.0 molar X and no Y, how long will it take to make the solution 0.36 molar in Y? Now remember, we've talked about this before. What is the key phrase right now that is standing out to you? And you go, duh, we've talked about this. The key phrase is how long. And every time they talk about how long, what are we doing? Every time they talk about how long, we're using the integrated rate law. Because integrated rate law relates concentration and time, right? And time is what we're looking at. Okay, so I go, this is good. I know that the reaction is first order. And I know I have to use integrated rate law. First order, and I have to use integrated first law. So I'm going to write down that equation. which is ln. X is my reactant. That's times T. This is initial. Equals minus KT. So far, so good. Now, I want to remind you of one thing. If you remember, we said this is initial. What does this one mean? That means left, right? That's how much is left. Don't forget that, okay? Now, what I got here, I have 2x going to y. So I have 2x, let me make it a little bit, going to y. At time 0, at the very beginning, what's going on? At the very beginning, what do I have? At the very beginning, I have, how much of x do I have? I have 1.0 molar x, and I have none of the y. Okay, you following me so far? Now, at time t, you can call it whatever you want. At time t, what happens? I have 0.36 molar y, but I don't know how much of the x I have. You guys are good so far? Okay. So, what am I going to do? What am I going to do? Now, remember, I have to plug in this equation. What I want to figure out is t. Pay attention over here for me. K, well, I have k from over here. That's not a problem. I have the initial. That's not a problem. But I need to know how much of the x is left over. That's really key. I don't have that right now. But could I figure it out? I could figure out because I know how to use hashtag mole ratio, right? I know how to use mole ratio because if you look over here, they give you y at times t. And what y is 0.36 molar of y. Now, I can do a mole ratio. We talked about hashtag mole ratio. I don't want the moles of y. What do I want is moles of x. What is the mole ratio? Remember, coefficients are the mole ratio. Coefficients are the mole ratio. So it's going to be 2 to 1. It's going to be 2 to 1. Now, if I do that, what I end up getting is 0.72 molar of x. Okay? Again, I know 0.36 was formed. I can do a mole ratio, you know how to do that, to figure out how much x was what? How much x was used. Because you have to use x in order to form y. You have to use x in order to form y. Now, the problem is, used is not what I want. I want to know how much is left. Well, that's not bad. All I have to do is subtract how much I started, which is 1.00 molar, how much I used, which is 0.72 molar, and what I get is 0.28 molar that would be left. You guys follow that? So this is how much I started, this is how much I used, and then what you end up getting is how much you left. Let me put it here. Okay, not bad. Now I have every single piece of information now to plug in here. I have every single piece of information to plug in here. Now let me go here so I can write it neatly. Help me out. So how much of x is left at times t? 0.28. 1.0 is initial. Minus my k is 0.231, and I'm trying to solve for t. When I solve for t, when you solve for t, I get 5.5, what's the unit? Minutes. 5.5 minutes. This was a good practice problem, right? To kind of go back to integrated rate law and figure these kind of questions out. Again, the only tricky part is you have to remember when you plug into this equation, this is x at times t. How much x is left at that moment? That's what you need to figure out. And sometimes you have to do stoichiometry, the good old mole ratio, in order to do this. Okay, beautiful. We did a lot of practice problems today. I feel pretty good about today. We have only one more thing, mechanism, to talk about, and then we're done with kinetics. I will see you guys next time.